Okay, this is the second part of this lecture 8 that I had to make it asynchronous for you. If you remember, I said that we come up with three equations right now that and these three equations, this is for the length scale, Kolmogorov length scale. This is for the Kolmogorov velocity scale, and the third one is the Kolmogorov time scale. So these are actually expressed in terms of Reynolds number, and the Reynolds number based on the uh, largest scales. So this is the Reynolds number that is defined based on the fluctuations and the length scale of the largest scales inside the fluid. So you have to keep these in mind um, in order to have an estimation of the Kolmogorov scales in the turbulent flow. Normally, we know that viscous effects are very dominant at very low Reynolds numbers. So, based on this definition, if the Reynolds number is low, means that the viscous forces are very large. And then inertial effects are very dominant in the high Reynolds numbers, vice versa. Now, if viscous effects, I mean the frictional effects, are very dominant, this means that Reynolds number associated with the smallest eddies should be very small. How much is it? Actually, we can define the Reynolds number for the smallest eddies in the domain. So that Reynolds number before we had, like this here, this is the based on the largest scales. But for the smallest scales, we define Reynolds uh, subscript eta, base Reynolds number based on the smallest eddies, and it is equal to actually the uh, length scale, velocity scale, and divided by viscosity. Now that we know the length scale and the velocity scale, we can substitute, and when at the end of the day we will find this. So the Reynolds eta is the Reynolds number of the smallest eddies in the domain. And this equation in here does not mean the Reynolds number of the smallest eddies is equal to 1. The order of magnitude of it is 1. Okay, so it means if you are one of those very, very smallest eddies, these eddies, you would feel yourself inside a very, very high viscous flow, like you would feel yourself inside honey. Sometimes we call these very low Reynolds numbers, if you remember, as creeping flows or a Stokes flow. So the Reynolds times Reynolds inverse is equal to 1 means that it is in order of 1. So it could be maybe 2, 5, but it's not 1,000, it's not 10,000. Okay? We can conclude that in general, in these scales where we have the smallest eddies, the flow field is very stable, meaning that these small eddies that you have, the Kolmogorov scales in here, could be subjected to some disturbances, obviously, but all those disturbances will get damped out very quickly. If they, for example, somehow get disturbed, they can disintegrate and just disappear, and whatever energy, like kinetic energy, they might have, it will just turn into heat, and then the eddy will be vanished. All these exercises plus the stories I told about the life of an eddy can be summarized in this sketch like this in here story. So on the left hand, we have the smallest eddy size. So in here we have the smallest eddy size. And on the right hand we have the actual geometry. It could be the actual geometric length scale of the object which generates the turbulent flow. Whatever it is, it could be diameter of a jet, diameter of a cylinder, the chord length of a wing, or the thickness bar of a turbulence grid generator inside your wind tunnel, anything. In reality, the largest eddy sizes are a little bit smaller than this actual geometric length scale. So it's not going to be exactly equal to the diameter of a jet, for example. The technical word for the largest eddy size and the smallest eddy size is, as you see, the integral length scale and the dissipation length scale, respectively. In the range between the smallest and the largest, something happens. Energy is getting transferred, as you see with these arrows, and eddies will break up and sometimes they merge. So generally, we divide the whole range into three parts. The region where you have the largest eddies, this is called the energy containing range, this green range. And this region is very heavily geometry dependent. The actual value of capital L in here and then the small l can be very different. And if you compare a wake of a cylinder and, for example, a wake of a full Airbus plane, for example, the turbulent kinetic energy, which is sucked in from the mean kinetic energy, uh, as we showed last week, is generated in here in the energy containing range, and that's why we call it energy containing. The second range is called the inertial subrange, and the third one is, which is close to dissipative scales, is called dissipation range. We know from Kolmogor's hypothesis that the physics of the flow basically is determined by nu and epsilon, viscosity and the dissipation rate in the dissipation range. But in the inertial subrange, the energy does not disappear. It is energy disappears to heat in the dissipation range. Okay, because of the action of the viscosity. But viscosity is not in the inertial subrange. It only gets transferred to the smallest scales by the inertial action. So inertial subrange is only governed by dissipation, this rate of dissipation. If you remember, we had the production term, and it's in here in the K equation. So let's go back to your notes. In the turbulent kinetic energy equation, you see the production. This P generates actually turbulent kinetic energy, which is generated by the a small l, these eddies, the integral length scales. And as a part of the eddy breakup process, this energy gets transferred all the way to the smallest uh, length scales and then loses that energy by both viscosity and dissipation. So at this point, we have an idea about the order of magnitude of the smallest eddies, largest eddies, how energy is produced, what's the relevant equation for that production, how it is transferred, and how it gets dissipated, and what physical parameters govern this process. Okay, there is one final thing that uh, we know, we have to understand this point in here. This energy is generated, we said, through production, and it's transferred down to smaller scales. So, how is this total energy distributed within this whole range? Let's say whole range from this L to this eta, how the energy is distributed. Is it uniformly distributed, or it is changing? I mean, in some parts we have low energy level and somewhere else we have high energy levels. The distribution of energy among length scales uh, from eta to L range, is called the energy spectrum. If we talk about, for example, light spectrum, you have heard about the light spectrum. We know that light can be considered as a wave, right? So we say the spectrum is composed of different colors, but in reality, each color corresponds to a certain wavelength. For example, in here 532 nanometer is the green light in here, for example. So that distribution of wavelength, or in our case, distribution of a scale length, uh, because both have the unit of length, as we know the wavelength is nanometer meter. So we have this distribution of mm, lengths. So we want to know how the energy is distributed in this spectrum of length scales between uh, capital L to eta. So what we are talking about is a turbulent flow signal, right? I know that it's a fluctuating signal. So as you see in here, the instantaneous velocity, you have like this fluctuation, and it's fluctuating around the mean value. You have this orange mean value in here, and if you subtract the mean value, it is a fluctuation around zero, like what you have in here. So it's fluctuating around zero. This is a typically statically random or a stochastic signal. Okay, and just to remind you, a statistically stationary process uh, means that the statistical properties like the average, the variance, the skewness, flatness, and other things do not change with time. In addition to those, we have defined some other parameters like autocorrelation, the autocorrelation function, and so on and so forth. In general, regarding a time variance, uh, like this signal that is varying in time, the simplest multi-time statistical variable is called autocovariance function. So what is this? It's um, velocity at some time multiplied by the velocity um, at some time plus s, and then get averaged. So let's say this is shown as an example for you. So you select some time and you select some t plus s. You will have two values of velocities. You take those, multiply those, and then get averaged. So this is an averaged value. In other words, you go to time t, get the ut, and then at a certain time later, t plus s, you have this ut plus s, and in statistics we call this s as lag. Okay, this is called lag. So you multiply these two and get one number. Then you go to another time like t prime, and again using that certain lag. So this s is constant, the lag is constant. You will have the velocity at t prime and then u at t prime plus the same lag. Then again multiply these two and so on. And then you get the average of all of those. So this average means that thing. Uh, and then you will obtain this R, which is your autocovariance function. If you normalize this autocovariance function, you will get the autocorrelation function. So how do you normalize it? Um, the numerator is the autocovariance function, and the denominator is your variance. So u squared bar. So variance is nothing but the autocovariance with zero lag, right? If you have the uh, zero lag, meaning this S is zero, then you get the variance. So uh, it's clear. Some of the autocorrelation function properties are listed in here. So first of all, the rho is the autocorrelation function, which is normalized autocovariance function. Rho 0 is equal to 1. The magnitude of rho 0 is smaller than 1, or it always gets values, some value between -1 and 1. And then the rho s is equal to rho minus s, which shows that it is an even function as it is shown here. So if you actually draw the variation of autocorrelation function versus s here, you get something like these curves, like the Gaussian distribution. It is a symmetric function around 0 and has maximum at 1. And the plot of this rho s versus s is called parallelogram. So this is a parallelogram. As a typical example, these two distributions you see of autocorrelation function are obtained from two different signals. For example, one signal gives me the blue one, another signal gives me the orange one. And you see that they do not they do not give the same information from here. The blue distribution says that even if you keep increasing your s, I mean lag, to large amounts, you still have certain level of correlation, right? I mean, it means that you still have some certain level of rho. But in orange one, if you keep increasing the lag, the correlation will be lost, right? Here, the correlation will be lost. I mean, after this point, there's no correlation. Meaning that if you go to larger and larger separations in time, the data that you recorded in this range separation are not correlated at all. This is kind of related the to all this scale physics that we discussed. If you remember when we first introduced autocorrelation function a few weeks ago, we said that it can be used to estimate the scale information. All the scales that are present in the flow field, they are the main reason behind the fluctuations, and if there is some correlation in the data, it can be quantified using those correlation functions. If the same scale is responsible for a certain size or size range or generating the same signal, it can be estimated from these plots. Because we are not dealing with a completely random signal. Remember that if I plot a parallelogram using Excel, for example, I use a command in Excel random. I couldn't come up with those nice plots that I got from real velocity data. So these belong to the real velocity data, not the random data. So it's not either white noise or a stock market. It is filled with eddies. You're taking uh, a signal from some physical phenomenon. And these eddies are generating these fluctuations. Therefore, all these fluctuations in velocity or in pressure should be related to the size of the eddies. That's the main idea of this discussion. So if I somehow able to calculate these functions using the time or spatial signals that I have recorded, how do I estimate the size of the eddies? Now, this is the question. We calculate the area under this rho SS or parallelogram curve, and then in time series, the tau bar, which is the integration of rho s, um, is called the integral time scale. This tau bar, integral time scale of the any stochastic process. Our stochastic process is turbulence, so we call it integral time scale of turbulence. According to the Pope's book, in reality, we integrate up to the first uh, crossing T0 of the autocorrelation function. So first crossing, we will see it in a moment. Don't worry. What we are interested in turbulence studies is if there is an eddy occupying a certain space and it is traveling with the flow. Let's say you take a snapshot and you see an eddy in the region that is occupied by that eddy. Let's say this is a large eddy, and we are not talking about very small eddies right now. In the spatial range, any 2 points have to be correlated, right? The range within the range that the eddy is occupying. I'm not talking about time correlation here. Any 2 points that are within the same region occupied by the eddy have to be correlated. And logically, the correlation of a point inside the eddy and a point outside should have a smaller value. So, for example, in this figure that you see, yellow and green points are within the eddy, but the red point is outside the eddy. So it has a lower correlation value with the two others. This type of correlation is called spatial autocovariance, which is known also as 2 point correlation, because we are interested in not time separation but spatial separations. This is the simplest statistics that you can get from the velocity data. Of course, you need to have a data which is generated by direct numerical simulation or experimental data, and the field data can be obtained by particle image velocimetry. If you have point measurement techniques like hot wire anemometry or laser Doppler anemometry, you cannot get 2 point correlation, because what I'm showing you is the instantaneous distribution of the flow. The eddy shows up in the instantaneous flow, not in the averaged flow. So the only way to get the instantaneous field data is um, to use PIV experimentally or doing DNS numerically. A special autocorrelation, so this 2 point correlation, I mean, is the simplest statistics containing information on the spatial structures of the random field or turbulent field. The spatial autocovariance function, uh, I mean, this 2 point correlation is defined um, as a second order tensor, Rij. So this Rij is a function of R. R is the separation between 2 points. X is the position in the space. So this, you see this R in here. This is the separation between the two points. And of course you have time, so it is a function of time as well. And it is also called 2 point one time autocovariance, because you have 2 points. One point is at x, another point is at x plus r, and it is at one time. Or in short, we call it sometimes 2 point correlation most of the time. And it has to be a second order tensor, right? Rij, because it involves three components of velocity vectors, plus I see the r, which is the separation, which is a vector, and it does have then 3 by 3. So uh, you see the velocity at some vector times the velocity at some another vector. So 3 by 3 equal 9 components, and it is statistical averaged, right? So you see this bar sign for each instantaneous velocity field. I mean, each snapshot, if you take t out, you do the multiplications everywhere and then get average of all those multiplications. Consider an eddy which is marked in the flow. For example, in here, you have an eddy. It travels with the flow, and if this eddy is not distorted, in other words, at some delta t time, seconds later, I moved my camera to the right and get another snapshot. And if I have exactly the same shape, see, the shape is the same, exactly the same shape of this eddy, this is what we know as a Taylor's frozen turbulence hypothesis. So we are talking about the Taylor's frozen turbulence hypothesis. G.I. Taylor first proposed this. So he said that ddx is almost equal to 1 over u bar ddt. So this u bar is the local mean velocity of the flow. The idea is this. Let's say I have a wing like this, and I want to know different boundary layer characteristics on the wing. I want to calculate it, and there is some free stream turbulence. So the incoming flow has some free stream turbulence, meaning that it has some eddies which are traveling towards the wing, while they are traveling in a certain, for example, delta t time, not necessarily the whole time, just a small time, delta t time. They may keep their shape like this, what you are seeing in here, those eddies, those incoming eddies. In many engineering applications, we have to use this actually hypothesis that eddies preserve their shapes along a small delta t time. Because most of the time, if we don't have the PIV data, we don't know the spatial distribution and those spatial structures. And the only thing that we know is is there must be some spatial structures. We don't know their shapes, but we know that they are traveling with the flow. So if I assume they are traveling without changing their geometry or their shape, therefore you can record the time variation using a hot wire, do the autocorrelation analysis, and estimate the size of these traveling eddies. The Taylor's frozen turbulence hypothesis is the first level of approximation to understand the general spatial structure of the flow. And these days, with the help of PIV, we do the estimation of the eddy sizes much better. In terms of experimentation, most reliable technique was hot wire anemometry most of the time, And PIV allows us to take snapshots of the instantaneous flow where we can see the eddies themselves and how they travel. If they distort their shape, we can see that using the PIV.